In this experiment, we're going to apply skills we learned in experiment number 2 to determine the density of aluminum foil. Goals. In this lab, we're going to continue our focus on building a laboratory safety mindset by practicing wearing appropriate personal protective equipment in the lab. We're going to collect some data using the same common laboratory equipment we learned to use last week to determine the density of an irregularly shaped object. We will then analyze our results to determine the accuracy and precision of our measurements. And last, we're going to work through some multi-step problems using dimensional analysis. Numbers and units. Numbers. When working in the lab, the numbers that we use are not made up. Instead, the numbers we use come from physical measurements we perform in the lab. In this lab, we're going to be measuring physical quantities like mass and volume. The reliability of these measurements depend on two things: the quality and accuracy of the instrument or glassware we're using, and the skill of the experimenter. We learned in the last experiment how to make measurements using the analytical balance, graduated cylinder, and burette. In this lab, we're going to use those skills to make some more measurements. The significant figures we use in our calculations come directly from measurements that we took in lab. You'll need to spend some time studying your equipment to determine how many significant figures that particular device uses. You should always record all the significant figures you have when making measurements. For example, when using the analytical balance, if it has 4 decimal places for the mass, you should write down all the decimal places, even if you think you're probably going to be rounding to one significant figure. Again, it's better to have too much information than not enough information. When looking at glassware, you should always estimate one additional decimal place beyond the markings on the glassware. Always assume that the last digit is in fact an estimate. Let's look at an example. I've got some markings drawn on this graduated cylinder. So you can see that it goes up to 2 milliliters. And then we have 2.1, 2.2, and 2.3. And it looks like it's precisely on that line. So we're going to write down 2.30 milliliters, with that zero being estimated. Remember, we always estimate one decimal place beyond the markings on the glassware. And if you don't remember them, you probably need to review the significant figures in your textbook. There's a few things you need to look at, including non-zero digits, zeros, dealing with the exact numbers, things like there's exactly 12 inches in a foot, the addition and subtraction rules, and multiplication and division rules. Units. An important part of taking measurements and recording data in chemistry lab is looking at units. For almost all numbers you're going to record for this course, you need to write down the units that go with them. Without the units, the numbers are meaningless. In general, most of the equipment that you will use in lab has the units written down on it, so you can easily identify the unit of measure. Without the units, most numbers are meaningless. If I have the number 4 written down, am I talking about 4 grams, 4 milliliters? What does it refer to? Always include the units. This will also help when you're doing problems. Many of the problem-solving skills you'll need come from looking at the units you're given and looking at the units you need in your answer and figuring out how to get from one to the other. Let's look at an example. How many inches are in 2.5 miles? When I'm faced with a problem that looks like it's going to be involving unit conversions, I start by writing down all the different conversion factors I know involving the units given. So in this case, I've got inches. I know that 12 inches equals 1 foot. I know that 3 feet equals 1 yard. And I know that 5,280 feet equals 1 mile. Now, it may be that I write down a conversion factor that I'm not going to end up needing, but it's usually easier to have all the things I might need written down before I start the problem. So we're going to start out with looking at the number of inches in 2.5 miles. So I'm going to start with that 2.5 miles. I know that miles is going to be on the bottom in the next fraction, so it will cancel out. So the best conversion factor for that will be to have the last one we wrote down, the 5,280 feet equals 1 mile, so that the miles cancel out. Okay, so I've got feet, so I know I have that one on the bottom, and I'm trying to get to inches. So if I look at what I wrote down, I see I have a conversion factor directly from feet to inches. So 1 foot equals 12 inches, and I see that our feet cancel out. So the only thing I'm left with now is inches. And to find the answer to that, I just need to multiply across. So 2.5 times 5,280 times 12, and I get 158,400 inches. Now the next thing I need to do is write this number in the correct number of significant figures. And if we look back at our values used, well, we know that 12 inches is an exact number, so that isn't involved in our sig figs. And we look back at our original number in our problem, which is 2.5. So this tells me that I need to give 2 sig figs in my final answer. Well, the only way to do that with such a large number is to use scientific notation. So I'll write 1.58 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5th inches, and then round this to 1.6 times 10 to the 5th inches. This will be my final answer. Notice that I have the correct number of sig figs and that I've included the unit in the answer. As it turned out, I didn't need to know the conversion from 3 feet to a yard, but that doesn't hurt to have a little bit of extra information. Precision versus accuracy. We're also going to be evaluating 2 different things in this experiment, precision and accuracy. These 2 things mean something very different. Precision means how close your values are to one another. So if I record the mass of a sample 5 times and I have a very low standard deviation, I can have high precision. That tells me that all my values are very close to one another. Accuracy tells us how close our values are to the accepted value. Percent error is a great example as it compares the accepted value to your experimental value. So if I have a low percent error, that tells me that my experimental values were close to the accepted value. Let's look at precision a bit. If we were to measure the same sample multiple times, our results should be the same. However, sometimes our results aren't. If I were to go into lab and fill up a graduated cylinder between 5 and 6 milliliters, like I'm trying to measure out some volume for multiple test tubes and record the result, I'll be making the same measurement multiple times and determine the average value. As our measurements are made, you can begin to see they aren't always the same. There's some amount of variation. Calculating the average can tell us some about the variation, but the standard deviation is a true tell. As I calculate that out, you can see that the standard deviation changes as I make additional measurements closer to the 5 milliliters. My standard deviation becomes larger simply because my first 2 measurements were near 4 milliliters. Also, please keep in mind with standard deviation, you can only report standard deviation to the first significant figure, and whichever decimal place that is will tell you where your average starts to be imprecise. Meaning carrying a bunch of decimal places in your average and in your standard deviation is completely meaningless. The glassware and equipment that we choose to make our measurement with will determine the accuracy of our measurement. Volumetric flasks are designed to accurately hold 100 milliliters of solution. You'll see as I pour the solution into the 100 milliliter graduated cylinder, it's roughly as accurate as the volumetric flask. This is not true as I pour this 100 milliliters into the 100 milliliter beaker. You'll see that it's almost full. And when that gets into the 250 milliliter beaker, these are much less accurate measuring devices and should not be used to perform a measurement. If, on the other hand, you have some kind of known value for your measurement, for instance, like the mass of a standard weight and your measurement, you can calculate a percent error. The percent error is defined as being the accepted value minus the experimental over the accepted value. And you're going to take the absolute value of that. So let's look at an example. If I measured out 4.35 milliliters instead of the 5.00 milliliters expected, what is the percent error for my measurement? The first thing we want to do is identify the accepted value from the experimental value. The question itself gives us some clues, as it identifies the 5.00 milliliters as the accepted value, and we are told that the 4.35 milliliters was measured out, an experimental value. We then simply plug those numbers into the percent error equation. 5.00 milliliters minus 4.35 milliliters divided by 5.00 milliliters. Then take the absolute value times 100%. That gives us 13%. Density. So now we're getting to density, which is what we're actually going to be determining for aluminum. We're going to use the mathematical combination of mass and volume. In general, for most liquids and solids, it's reported in grams per milliliter. Density is an intensive property, meaning it doesn't matter if I have 10 milliliters, 100 milliliters, or a liter of something. If it's the same solution, the density will be the same as long as the temperature is constant. So for example, water has a density of 1.00 grams per milliliter at 20 degrees Celsius. This does change with temperature, but only slightly. So how are we going to measure volume? You may remember from your math class that you can measure the volume of an object by measuring its dimensions, or its length times its width. If we have a cube, it's pretty easy. We can use a ruler to measure a cube's length, width, and height. But what if the object is very thin or has an irregular shape? In that case, we need to measure the volume by displacement. You can put some liquid into a graduated cylinder and record the initial volume. You can add the object, watch the height of the volume of water change in the graduated cylinder, and then you can measure the volume of liquid after. The change in volume of water or whatever solution you're using will be the volume of the object you placed inside it. There are a couple conditions you have to be concerned about when measuring volume by displacement, because it can happen. The liquid must not be one that will react with the solid in a time frame of the experiment. So if something is very slow reaction over a few days, it'll be okay to measure it in there for just a few seconds. And the density of the object must be greater than that of the liquid. If the solid is floating on the top of the liquid, then you are not truly measuring the exact volume of that solid. So you have to make sure that your solid will sink in the solution or the liquid that you're using. We can also determine density using the graphical method. Let's look at this example graph with some mass and volume measurements already recorded. If we look at the data points, we can see that we have mass on the y-axis and volume on the x-axis. Remember that the equation for the line is y equals mx plus b, and that m is the slope. Rise over run is the change in y over the change in x. So when we're looking at our graph, if we look at the slope, we're going to have mass over volume, which is the definition of density. So when we look at the formula of a line, we see that we have m, that's slope, which then is the same as density. If we look at our graph and we look at the data that we're generating with this graph, the slope will be the density of our sample. Writing your own procedure. Now for this experiment, you'll need to write a procedure. So the best thing to do is to start by reading the introductory material and to read the data analysis questions to determine the data that's needed to answer those questions. You will need to pull in what you've learned in experiment 2 about how to use lab equipment that's available in the lab. Start by making a list of all the information you need, including things like density. To find density, and you'll need mass and volume. Think about some of the following things. Measuring multiple sizes of multiple samples. Think about what would the graph look like if the pieces of foil were all the same size. That is, the pieces would have the same mass and the same volume. The shape of the foil, does that matter if you crumple it up in a ball and roll it up? What type of glassware are you going to need? Are you going to use a beaker or a graduated cylinder? And if so, what size of glassware? As a general rule, you always want to use the smallest glassware possible, as it tends to be the most accurate when dealing with the volume you're measuring. You do need to write down the procedure with enough detail that someone else could repeat the experiment with only your procedure and get similar results. Explain each step you take. If you record the volume by displacement, explain how you do that. It's okay to change your procedure as you're doing the experiment. It's only the final procedure that goes in your lab report. So if you get into lab and realize there's something not working the way you thought it would, make the change, write it down, and include the change in your final version. You also need to keep a lab notebook. The best thing to do is before you come into lab is to set up that lab notebook. You're going to need tables for your data, such as your mass and volume pairs for different samples. Set up the table, make a list of the data you need. Write in the units, draw lines or boxes where you're going to fill in numbers. The goal is when you come to lab, you're just going to fill in the numbers without having to write a bunch of information down. This will save you a lot of time and frustration because it makes sure that you have all the information you need before you leave class. There are example pages in your lab manual showing what lab notebooks should look like before you come to lab and after you leave lab. Please look at these examples. Just like with the procedure, it's okay if it's not perfect when you come to class. Make a single line to mark out the incorrect information and rewrite the new information. Lab notebooks are meant to be the original record of your data and should be just that. Don't feel the need to rewrite them, to write on scratch paper, or to copy it into your lab notebook later. Just record the information directly in your lab notebook. Experimental notes. Reminders. A few reminders for this experiment. First, laboratory safety must always be followed. You must wear your goggles the full time you're in lab. If they fog up, please step out into the hallway and wipe them off. Do not take your goggles off while you're in the lab room. You are also required to wear your scrubs in lab once they've been handed out. Second, and get in the habit of writing down the actual masses and volumes used. Don't spend a lot of time trying to get measurements that are exactly what's shown in the lab manual. Instead, get close and write down precisely what you used. Remember, for liquids, you should always estimate 1 decimal place beyond the markings in the glassware. For example, if you're using a 10 milliliter graduated cylinders with markings to the 10th mark, you can actually get 2 decimal places. Third, use distilled water to avoid introducing any kind of impurities into your experiment. And finally, don't forget that you need to return your glassware clean and dry to your lab drawer. Waste disposal. All the chemicals we're working with this week are non-hazardous. Water can be poured down the drain and your aluminum foil can go into the garbage can. Please make sure, however, that you are careful not to leave any aluminum foil in the sinks or stuck in the graduated cylinders. Please be aware, starting with the next lab, the level of hazard will increase, so please make sure you start learning and applying proper safety and waste disposal now. Hints for success. A couple of last hints for you. First, come prepared. For this lab, you're writing your own procedure and one will not be provided for you. I know this is scary. However, you can draw on what you learned in experiment 2 and what's in the background reading for the lab manual for help. The TAs are also available to assist you. Make sure you identify what measurements you'll need so you have space for them already indicated in your lab notebook. You'll also want to look at the questions in the analysis section to see what questions you'll need to answer. Then think about what information you need to answer those questions and work backwards, thinking about the data you need to collect in the lab to be able to work the problems. If you have any questions, please reach out to your teaching assistant, speak with the TA in the General Chemistry Learning Center in Jacob Science Building, room 219, or send me an email.